Hello friends, welcome to a lecture of inner product space. We have earlier studied definition of inner product space, some examples of inner product space and norm of a vector we have studied, some lemmas we have proved. In this lecture we shall study what is Schwarz inequality, and before studying Schwarz inequality or before proving this Schwarz inequality, we will prove this lemma. I have written it as a lemma number 2 because we are going to use this lemma to prove Schwarz inequality. The lemma 2 is if A, B, C are real numbers such that A is greater than 0 and this quadratic expression A lambda square plus 2B lambda plus C is greater than or equal to 0 for all real numbers lambda, then we have the relation B square is less than or equal to AC. So, this we shall prove first, and for proving it is easy to prove this relation, we shall consider this expression, quadratic expression, and we will express this in complete square form. To write the term in complete square form, to get complete square term, we can write this expression A lambda square plus 2B lambda plus C. This is equal to, we divide and multiply by A inside this expression, or C, this will be A square lambda square. We have divided and we are multiplying plus here 2AB lambda, and C, to make it perfect square we should add the term B square, so that this expression will be a perfect square, and we have added B square which is not here the term, and therefore we have to subtract this term, and this C is there, we have to write that term C. So, I shall write C minus B square upon A. Now, C we have not changed the value, only we have added B square upon A and we have subtracted B square upon A in this expression, so as to complete the square. So, now this is a complete square of A lambda plus B. So, this is equal to, this is 1 upon A lambda plus B and its whole square plus C minus B square upon A, and we shall suppose this expression as 1, and we are given that this is greater than or equal to 0. So, this is greater than or equal to 0, that means this expression is greater than or equal to 0, and we shall suppose this as 1. Now, what we shall consider is this expression, it is given that this expression is true for all real number lambda, since this expression 1 or the relation 1 is true. The relation 1 is true for all real numbers lambda, all real lambda. Therefore, it is true for a particular any value, and that value we should select as lambda is minus B upon A, that we shall select. So, this is true for all values real value lambda, it is true for lambda is equal to minus B upon A. In particular, it is true for lambda is equal to minus B upon A. So, why we have taken lambda is minus B upon A? Because if you put lambda is equal to minus B upon A, then this bracket becomes 0, and we can put this in this expression because it is given, it holds for all real values of lambda, and this is a real value of lambda because B and A are real, A, B, C are given are real, and therefore that is a real value of lambda, and again A is greater than 0. So, therefore this is defined, and thus putting this in 1 we get. So, putting this value of lambda in 1, or in particularly the right side of 1, putting this value of lambda in 1, we get. Now see, we shall put this value in this part only, and this is 0. If you put lambda is equal to minus b upon a, that is 0. So this first term is 0 and second term is only, so we get c minus b square upon a is greater than or equal to 0. We get c minus b square upon a is greater than or equal to 0. Now we can multiply by a throughout this inequality because a is greater than 0. Since a is greater than 0, multiplying by a, we get this will be ac minus b square. We are multiplying by a, and this is greater than or equal to, the inequality remains same because a is positive, and 0 into a is again 0, or this means ac is greater than or equal to b square, or that means b square is less than or equal to ac, and this proves the result. So this is what we have to prove, b square is less than or equal to ac. So the result is simple, this proves the lemma, or this proves the result. And now we shall state what is the Schwarz inequality as our first theorem. Now the theorem number 1. Schwarz inequality. The inequality is statement is simple. If u and v are vectors in V, then we have magnitude of the inner product or modulus of this inner product is less than or equal to norm of u into norm of V. So this is the Schwarz inequality, which is important in mathematical analysis, whether complex or real. So this is magnitude of inner product u and v is less than or equal to norm u into norm v. We have defined earlier what is norm u or norm v, and now we shall prove this. Now if what happens if u is equal to 0, that we shall first state. If u is 0, a vector u is 0. If u is equal to 0, then both the sides will be 0. Then the inner product of a vector with 0 is always 0. So then we have then both of these sides, then both the inner product of u with v is 0 and the norm u into norm v is also 0, and the result is true, and thus the result is true in this case. And this happens for same for v is 0, either u is 0 or v is 0, the result is true. Now we shall assume we are considering only the first vector here as u, we can interchange the role, and u is 0. Now we shall consider u is not 0, then the inner product will not be 0. But there are two cases, the inner product is either real or the inner product is complex. We shall consider these two cases one by one. Now the case first we shall consider as, let the inner product of u and v is real. So we shall write that as case 1. Let the inner product of u and v is real, or let us suppose is real and u is not equal to 0. This is our first case. And here we will consider for all values of lambda, real values of lambda, we want to use this corollary. Then for all real lambda or all real numbers lambda, we have we now use our lemma 1. We have by lemma 1, and the non-negative property also. We have, see, this 0 is less than or equal to. We shall consider the combination of this alpha u plus or lambda u plus v, lambda u plus v, and inner product of lambda u plus v with itself. This we shall consider. And you see what is the lemma 1 we have proved. It is actually this one. We have proved it in our earlier lecture. Alpha u, combination of alpha u, beta v, inner product of this with itself. And this is the lemma that we have proved in our earlier lecture. We want to use it here. So how to use it? In place of alpha it is lambda, and in place of beta it is 1. So therefore this inner product I shall write here on this right side of this expression. 0 is less than or equal to this. Why 0 is less than or equal to this inner product? This is our second property in the definition. We have any inner product u and v is greater than or equal to 0. That means 0 is less than or equal to any inner product, and this is the inner product, therefore it is non-negative, and therefore 0 is less than or equal to this. And see, it is alpha, in place of alpha here it is lambda. So this will be lambda bar conjugate, and inner product of u and u plus. Now what next is lambda into conjugate of beta. Beta is 1. So conjugate of 1. So that is conjugate 1 is can be written like this, but it is real. So conjugate of 1 is again 1, and u into v. That means inner product of u and v plus. Next is conjugate of lambda. That is conjugate lambda. And beta is 1, inner product of v and u plus beta is 1 into conjugate 1, and that is inner product of v and v. So we have used the lemma here, and we get this one. So but it is further equal to. Now you see, we can write this as 0, the extreme left side is 0 and these two are equal. So but the relation between this 0 and this is the less than or equal to, therefore 0 is less than or equal to this expression. And what is lambda into lambda bar? Lambda bar is again lambda, because lambda is real. For a real number this conjugate is the same. So it is lambda into lambda, that is lambda square. So lambda square, and this will be inner product of u with u plus conjugate of 1 is 1, so it is lambda into inner product of u into v, and conjugate of lambda is also lambda, so it is lambda into inner product of v into u, v and u. But you see, these are real, and in real numbers the inner product is commutative, that is inner product of u and v is same as inner product of v and u. Why? Because we have inner product of u and v is conjugate of inner product of v and u, but conjugate in the real number is same as itself. So therefore these two are equal. So these two are equal, and thus this these two terms become equal, because lambda is also equal to conjugate lambda, and this term becomes twice lambda into inner product of u and v, and the last is also 1 into 1, and that is inner product of v with v. So we can write the reason here as, since lambda and inner product of u and v are real, lambda is equal to conjugate lambda, and inner product of u and v is same as inner product of u and v is same as inner product of v with u. So therefore we get this relation. Now we want to use this lemma. So for that purpose we shall select C, a as this value, and we select this b as this value of the inner product, and c as this inner product. Now let, so we shall suppose this as first expression. Let a is equal to inner product of u with u, b is equal to inner product of u with v, and C is equal to inner product of V with V. So then relation 1 becomes, so I shall write here, the relation 1 becomes, then 1 becomes see what will be 1, that is 0 is less than or equal to lambda square into A, that is A lambda square, plus this is 2, this value is B, we are putting 2B lambda, and plus the last value we are putting as C, and this is the same as this expression A lambda square plus B lambda plus C, and this expression is greater than or equal to 0, or 0 is less than or equal to this. So it is the same, and therefore by lemma 2 we have B square is less than or equal to AC. By lemma 2 we have B square is less than or equal to AC. But what is B square? B is this inner product, that is so therefore B square means square of the inner product of U and V is less than or equal to A means the inner product of U with U, and into C means the inner product of V with V. So this is what we have, or that means now what is the inner product of U with U? By definition of norm, it is norm U square, or this is inner product of square of the inner product of U and V is less than or equal to norm U square into norm V square. This is the direct definition of norm U. Norm U is under root of inner product of U with U, and therefore inner product of U with U is square of the norm U. And now we take the square root, taking square root, and while we take the square root, these are lengths, and therefore we shall have to consider the positive value of the square root, and that means the absolute value of the inner product of U and V. We write like this, the square root of this, and this is less than or equal to norm U, it is a length and therefore it is positive, norm U into norm V, and thus the result is proved in this case, case 1, where this inner product is real. Now we shall prove the second case, that is case 2, where the inner product we shall assume as complex or not real. Second case, case second, let we shall suppose the inner product be alpha, alpha is equal to inner product of U and V, and alpha is equal to inner product of U and V is not real. It is not real, and if it is not real, it is certainly not equal to 0. Then it is not 0. Then see, alpha is not equal to 0 because 0 is real number. So it is not real means it is not equal to 0. So therefore we shall consider this quotient U upon alpha is meaningful. Why? Because alpha denominator is not 0. So therefore the quantity is defined or it is meaningful. Now we shall consider the inner product of U upon alpha with V. So what will be this? The inner product of U upon alpha with V, and by the linearity property we can write this alpha outside. So it is 1 upon alpha into inner product of U and V. And what is alpha? Alpha is, again we have taken inner product of U and V. 1 upon inner product of U and V into inner product of U and V, and thus this becomes 1, or thus we have inner product of U and V. Now the use of the lemma we have done in the first case, so I can write here. So thus we have So this is the left side. Inner product of u upon alpha with v, and the right side is equal to 1. So thus we have the inner product of u upon alpha and v is equal to 1, which is real. So thus this is real. The inner product of u upon alpha and v is real. 1 is a real number, and if it is real, we can apply the first case. So this we have obtained in the first case. If this inner product is real, we can write like this. So by case 1, we have. Now we apply. In place of u, here it is u upon alpha. Magnitude of the inner product of u upon alpha with v is less than or equal to. So we are using this here. Norm of u upon alpha into norm of v. This we will have. And now further part I shall write here. This is our statement of the theorem, and I will write the next step in the proof here. Or we shall see what is a norm u upon alpha. This is a corollary that actually we have proved, or we can write it separately. Now we can suppose this as our second result. Now we have norm of u upon alpha. This is equal to under root of the inner product of u upon alpha with u upon alpha, or that can be written as under root of. See, we use a linearity property, and this will be alpha outside will be 1 upon alpha, but this alpha, if you take outside, then it becomes conjugate alpha. Alpha is taken from the second component in the inner product, second vector of the inner product, it becomes conjugate, and it is inner product of u and u. So that is, now see, this is equal to under root of this is mod alpha square 1 upon mod alpha square, and inner product of u with u is norm u square. Taking square root, we get this as 1 upon mod alpha into norm u. Actually this property we have this result we have proved as a corollary, first corollary. See, what was that corollary? We have proved this one. Inner norm of alpha into u. Norm of alpha into u is equal to mod alpha into norm u. In place of alpha, here it is 1 upon alpha. So it is the same result, but we have proved it independently. Now we use it in second. So we use it in second, and then we will get this as. So, but one more thing we should note is this is we have taken mod of this, and but its value is 1. So mod 1 is 1. So this I shall write as this side also I shall write this is inner product of u upon alpha and v. Absolute value of this is equal to 1, and because these are the same, absolute value of 1 is 1. So 1 is less than or equal to this, and now we use this expression here. So using this value in 1, so putting this in 1, not 1, 2, putting this in 2, we get see what will be the second. 1 is less than or equal to, and this is 1 upon mod alpha into norm u into norm v. This expression we have used here, and now we can multiply by mod alpha on both sides. It is a positive quantity, so this implies mod alpha is less than or equal to norm u into norm v. But what is alpha? Alpha is inner product of u and v, or alpha is inner product of u and v. U and v that we have assumed in the start of the second case, and that is less than or equal to norm u into norm v, and this is what is the Schwarz inequality. Thus, we have proved the inequality in both the cases. The first case is simple, that is u is 0, then it holds, and second case we have taken this as a real value, and the third case we have taken it is non-real value. So, this is the Schwarz inequality, and this proves the inequality, this proves the theorem. So, this Schwarz inequality is important in analysis, and see it can be applied in the first example of inner product spaces we have. See, so we can write as a remark application of this Schwarz inequality, or the case. So, we can use Schwarz inequality or apply applications of this. In Fn we have, or let, in Fn let, we have studied this example earlier. U is n tuple alpha 1 etc. V is beta 1 etc. beta n, and define the inner product of u with v, as we have defined this alpha 1 beta 1 conjugate of beta 1 plus so on alpha n conjugate of beta n. That means first these components are taken as it is, and its conjugate is taken, and they are multiplied. So, this is the inner product of u and v. So, what is by Schwarz inequality? So, we have this result, this is the result, and therefore, see what will be the absolute value of this inner product, that is we can write this is the Schwarz inequality, and or that can be written as the magnitude of the inner product is less than or equal to, what is norm u? Norm u is we shall consider this in the square form. If you consider this in square form, this is less than or equal to norm u square into norm v square, squaring both sides, and this implies, now what is the square of this we will write. So, we get this is modulus of this inner product, that is mod alpha 1 conjugate beta 1 etc. alpha n conjugate of beta n whole square is less than or equal to. Now, what will be the norm square means inner product of u with itself, and inner product of u with itself will be like this alpha 1 conjugate, that is alpha 1 conjugate plus so on beta, that both are same, u and v are same. So, beta will be replaced by alpha, last will be alpha n conjugate, and it's a square. So, this is norm u. So, actually it will be the same, because norm u square is inner product of u and u, and therefore, this is the norm u square, and similarly what will be norm v square, and in place of alpha we will have beta 1 conjugate beta 1 and so on. So, this is the meaning of norm u square norm v square from this u and v, or that will be. Now, what is alpha 1 bar? This will be mod alpha 1 square, and that is we'll have this left side as the same alpha n beta n conjugate square is less than or equal to. What is this first expression? That is mod alpha 1 square plus so on up to mod alpha n square, and this is in one bracket, and in another bracket it will be, this will be mod beta 1 square and so on. The last will be mod beta n square. So thus this is the inequality in this case, or this is the application of Schwarz inequality for this inner product. So thus in this lecture we have studied a lemma number 2, Schwarz inequality in particular, and how to apply the Schwarz inequality in a inner product that we have studied. Remaining part we will continue in our next lecture. Thank you for watching the lecture.